very pleased to have Donghui visiting us, this time from very far away from Penn State, which is halfway around the planet, all the way to come here to both attend our conference and to give us a colloquium. This is something which in the future we hope to have many more regular exchanges and visits. Donghui will be leading the astrophysics group at KIAS in the future. So we hope to have many more opportunities for closer connections. For those who don't already know his fame, he was a PhD with TU in Texas and was postdoc at Caltech and Johns Hopkins before being professor at Penn State and then at KIAS in Korea. For any who haven't been to KIAS, it's a great place to visit. I'm sure we get to visit Donghui and others at a place actually fairly close to here. In fact, there's a direct flight from Songshan Airport, 10 minutes from here, that goes to Gimpo Airport, which is still a long way from here, but it's at least a fairly convenient connection to make. I must say that I've been very impressed. To me, he seems like a young fellow, and so he's not that he's a senior professor now, but he, in my mind, was always one of these young rising stars that will be changing our future understanding of cosmology. I've been following many of his footsteps on quite a number of topics that Donghui has pioneered with collaborators. Wherever he went, he would raise the standard of the cosmology that gets done. So we've been following his work for many years now, and we look forward to his colloquium today. So please.
Can you hear me? Yeah. Thank you, Eddie, for a nice introduction. Today I'll give a talk about something very different from this work series about. The title here is Searching for Dark Matter Black Holes from LVK gravitational-wave detectors. When I present this in front of my friend, they say, I understand dark matter, I understand black holes, I understand gravitational-wave detectors, but if you combine all those words, I don't know what to talk about. So I hope at the end of this talk, I convinced you that they're all connected to give us a great hint about the physics of dark matter. So that's my goal here. So let me start by summarizing the physical status of the physical cosmology right now. This is one-page summary of cosmology. So we know that our universe is spatially flat and expanding, and the expansion is accelerating. And then we also know the pie chart of energy budget of universe. Right now, 72% of dark energy, 23% dark matter, 5% of atom. We also know the pie chart at the very early time when CMB was released from the hot plasma. And this is the summary. Although I present this number as if we know everything about the universe, in fact, there are mysteries. For example, dark energy and dark matter, those are not the name of answer, but the name of problem. So the bulk of the effort in modern cosmology is devoted to figure out the nature of dark energy, the time-fixed nature of dark matter, or to see if they are the result of modification of gravity. And today's topic, obviously, is about dark matter. The story began in 1932 with this person. He is Fritz Zwicky. He was a theoretical physicist from Swiss. And he went to Caltech, and then he started to look at the data. And he focused on this cluster. This cluster is called Coma cluster, which is about 100 megaparsec away, and right at the northern galactic pole here. This is the two-mass galaxy distribution, and that's Coma cluster. So here is a summary table about the numbers about Coma cluster. So in this picture, we're showing about more than 10,000 galaxies. 10,000 galaxies are clustered within 6 megaparsec size. and then velocity, the random velocity of these galaxies is about 1,000 kilometers per second. Means that these galaxies are on average moving this speed. And then if you know the size and then velocity, you can compute the crossing time, which is about 6 billion years, which is smaller than the age of universe. So the chance that these galaxies, 10,000 of galaxies, get here by chance is very low. So they are gravitationally bound state. Okay? Now if you count the stellar mass, because you can see the light here, and then assume some constant mass to light ratio, and then you get about 3 times 10 to 13 stellar mass. And then now you know the stellar mass, and then if you know the size, what you can compute is escape velocity. Right? And escape velocity based upon what you observe, and the size that you observe is only about 140 kilometers per second. That's a plus. Galaxies in this cluster are on average moving with 1,000 kilometers per second. But then, the velocity required to escape this gravitational system is only 140 kilometers per second. Combining all those numbers, Zwicky concluded that there must be a bulk of mass that we cannot observe. That invisible mass must be at least 98% of this mass, and they are invisible. That's 1932. Because of many complex reasons, some part of personal and some part lack of evidence, this discovery was ignored for the 40 years until Beryllium had rediscovered that by looking at the galaxy. So this is another galaxy. She did was she measured the velocity of individual stars that she can observe as a function of radius, so the distance. Distance from the center is 0 center, and then left and right, you can see that on one side moving one direction, another side moving another direction. That's rotation velocity. So that is the galaxy rotation curve. And then people also extended this rotation curve. And for another neighboring galaxy, M33, we have this nice picture that we use for the top, this kind of top. So inner part of this galaxy, we measure the rotational velocity by using the stars. Outskirt, we measure the velocity by using the Coulomb messenger, neutral hydrogen line. But the rotational velocity is ever increasing like this. And if you use the Keplerian law of gravity, what you expect by taking into account all the mass that we see is this dashed line. There's a gap, right? So the observed velocity that we observe is not consistent with the combining mass that we can count by light. Again, we have to have invisible mass. That's another evidence for dark matter. So we had invisible mass in the cluster, invisible mass in galaxy, or about the smaller cluster. In our local group, we have so many dwarf galaxies. This is dwarf galaxy Fornax, dwarf spheroidal, Sculptor, dwarf spheroidal, Carnina, dwarf spheroidal, Sexton, dwarf spheroidal. Wait a minute. What do we have here? Believe me, there is a dwarf galaxy. We figured out by dynamical measurement of velocity. So for all those dwarf galaxies, you can actually distinguish stars. So we measure the velocity of individual stars. Then we play the same game. As a function of distance from the center, we count the dynamical mass required to give rise to that amount of velocity. Yes, answer, as a function of radius, solid lines are for 1, 2, 3, 4, 5, 6, 8, those 8 dwarf galaxies, 7. Those are the velocity-based mass measurement. And the dotted lines are periodic mass measurement. We need dark matter. Not only we need dark matter, the invisible mass seems to dominate the density in the dwarf galaxy. So far, we have evidence for the invisible matter, but then this invisible matter cannot be baryonic. That evidence came from the cosmic microwave background. This is the fluctuation amplitude of hot and cold spot we observe in cosmic microwave background fluctuations. X-axis angular scale, 1 degree, 0.1 degrees, as you go from left to right, is the small length scale. Let's take a look at the amplitude. This is amplitude fluctuation, which is about 13 microkelvin squared. If you take the fluctuation amplitude, divide this by the mean temperature, 2.7 Kelvin, you get about 10 to the negative 5. In the cosmological perturbation theory, the linear method, we know that density fluctuation only grew by a factor proportional to the scale factor, or inverse of redshift. So CMB was fixed at redshift 1100. So but in between the CMB time and current time, density perturbation can only grow by a factor of 1,000. If you multiply 10 to the negative 5 to 1,000, you get 10 to the negative 2. That amplitude density fluctuation is so small, it cannot form such a galaxy. That's the case if we have all the material coupling to photons. That's the evidence that dark matters cannot be variant. So then it excludes the possibility that some baryonic matter like us or planet, we are dark matter. Right? We cannot train ourselves as a bulk of dark matter. So that the dark matter must be non-baryonic. So we have a couple of more evidence in astronomy about property of dark matter. One of the most famous one is the duet cluster. In this picture, we are looking at the colliding two clusters. This pink contour is a gas distribution, and then blue contour is a mass distribution. Red chased by replanting, and pink is from the X-ray. And then we see the galaxy distribution. Right. So this cluster is colliding to this cluster, and then have this shock. That's how we can figure out that those are two clusters. And then the key observation is that while mass distributions are centered around the galaxy distributions, the gases are pulled in the middle. So the key observation here is off-center between mass center and the galaxy center. From there, we can conclude that the self-interaction between dark matter particles must be less than 1 centimeter squared over ground, because we know the mass of this cluster. So if you divide by the mass of dark matter particles, you get the number of density. Basically, you're constraining this with n sigma v. So that's the astronomical evidence for dark matter. But then what about the particle nature of dark matter? So the people make this kind of diagram. So we have X representing dark matter particle, Sm representing stellar model particles. Depending on which way you put the time axis, you can interpret this diagram in 3 different ways. If the time axis going from left to right, that's two dark matter particles interact to annihilate with the standard model particle. We saw that in our universe, and then some indirect detection. If time goes from bottom to top, that is dark matter particle and standard model particle, they interact, and then they scatter. That's called a direct detection of dark matter. And from right to left, that is two standard model particles collide to form dark matter particle. That's a pair production at collider like LHC. So people are very excited about this possibility, and they even call this miracle. Let me explain. At the early time, the temperature of the universe is very high, means that dark matter number density is very high. That brings the interaction rate between dark matter very high. But then, as dark matter transit from the massless, the relativist to non-relativist particle, and the number of density drop, naturally interaction rate drops. So at some point, n sigma v, the interaction rate drops below the Hubble expansion rate. That means that those interaction freezes out. So that's what this curve is representing. So as we increase the interaction cross-section sigma times v, that drop, the freeze out happens later. So you expect to have less number of dark matter compared to the weak interaction case. So from this kind of argument, you can compute the relic dark matter abundance that was thermally produced in the early universe. And then you get this equation that people call wave miracle. Left-hand side is omega dark matter times a square that's determined by cosmology. And right-hand side is a sigma V interaction cross-section, and the G star is one number of relative degree of freedom at that time of mass, and then XF is for the unit number. The right-hand side is wholly determined by particle physics. And if you plug in the Wick scale, Wick interaction scale, then you magically get something like 21. That's what people call Wick miracle. So it seems that dark matter number density kind of naturally provided if there were coupled with something. But then, if this is really the case, can we find this thing, evidence of this thing in the local universe? To do that, we have to find a place where we have so much dark matter. And I tell you earlier, dwarf galaxies are not places where we have dominated by dark matter. Right? So what people did, and then normally the dark matter annihilation signal can come from dwarf galaxy and with the gamma rays band. So what they look at is Fermi gamma rays chi, and they stack the Fermi signal only around the dwarf galaxies where we know that dark matter is dominating the system. And they compare the signature, the stack signature around the dwarf galaxy with a randomly pointed 300 position. They are represented by solid and dashed line for different decaying channels. They don't find difference. It seems like, although this miracle is miraculous, really, but then we don't find the local evidence supporting the miracle. And for this one, direct detection, what people does, we want to see the interaction between dark matter and standard model particle. What we do is we prepare for the extremely non-interactive material, shield it, and put it in the ground, wait. Okay. And here the figure of merit is mass of the material times the time that we wait. Okay. And then as a function of dark matter mass, and then y-axis is the interaction cross-section. So as we add and wait more and more, and then we lower the limbo bar. Most recent result is coming last year from the Lux-Jeffling collaboration. So we are around here. By the way, the boundary is the boundary expected for the neutrinos. So the dark experiment, direct detection experiment, will soon turn to be neutrino effective. Means they will see the flow of neutrinos. Okay, that's the situation right now. So we have this mystery stemming from astronomy. So we have some invisible, non-varying dark matter. And so far, our particle physics colleagues tried various ways of detecting dark matter and didn't give us some conclusive answer. Okay. Cool. So now here comes LVK, gravitational-wave detection. That's the two LIGO and then Virgo, and then I put the one for camera, but they are joining as a collaboration. So we have LVK gravitational-wave observers right now. And this is what they have detected up until 03. Right now, they are running 04, the fourth operation run. And then as a function of the black hole mass, and then this is, I think, from the earliest to the latest. Time axis is right inside. I'm focusing on this low mass range, round 1. Then you see there are these orange dots. They call neutron stars. Not because we know that they are neutron stars with 100% confidence, just because this mass range is below 2 solar mass. Okay, what's happening here? And then, as you can immediately see, that we have so many events here in the heavy black hole merger, but then we have only few events here. What does that mean? Does that mean that we're not sensitive enough to those small black holes? This is not true. So this is a signal and noise curve that I plotted. As a function of frequency of gravitational wave, y-axis is the Hall spectral density. I plotted 3 noise curves. The upper one is the advanced LIGO now, means as of 2018. And magenta is advanced LIGO after full upgrade. I think after 04 to 05 we'll reach this limit. And then this red line, the bottom red line, is something called futuristic gravitational-wave detectors. And on top of these three noise curves, I plotted three signal curves. If you're considering two 10 solar mass black holes merger as signal above the noise, and that's why I observe them. One solar mass binary at 1 megaparsec away, which is about Andromeda distance. Noise is above signal. Good, you measure. Even 0.1 solar mass binary, 10% black hole, 10% black hole merger, we could detect it even with advanced LIGO as of 2018 if those binary black holes are within the Andromeda galaxy. So if we have perfectly matching frequency range, there's nothing preventing the detection of those events. Of course, the light black hole binary means that the signal of binary merger will be less loud. So for the black hole of 1% of solar mass, you can only reach out to Andromeda galaxy and little above. 10% of solar mass, then you can go to Global, so it's about 16 megaparsec away, like 10 times further away than Andromeda galaxy. But I mean, there is boundaries that we can detect those gravitational waves. But then why didn't we study that before? There's some theoretical prejudice here. So this is a plot from the Keystone black hole and time warps. That is the text I'm using for my intro black hole class. And here is what's shown here is x-axis as a circumference for the radius of the black hole, and y-axis is the mass of the stellar. So in this plot, if we assume that there's no stellar wind and no mass loss mechanism, and then we're dealing with fate of three kinds of stars. If sun dies means if sun ran out of all fuel, then it will collapse, and will be white dwarf. If Procyon is about 2 solar mass, that died and then it collapsed until it hit the line of neutron stars. And if Sirius is much heavier, then if it dies, then it will go to a black hole. The assumption there is no stellar wind and mass loss. That's a simplistic picture. But what's important here is there is this critical mass scale called the Chandrasekhar mass scale, which is about 1.4 solar mass. That is a boundary between white dwarf and neutron star. And the neutron star actually is around the same boundary mass. And then if it's greater than 2 to 3 solar mass, you can only then you can form black holes. And if you look at Chandrasekhar mass, it's very, very interesting quantity. Give and take all the unity parameters, Chandrasekhar mass is Planck mass over proton mass cube times proton mass. That brings us 1 solar mass. Planck mass, we all know that, is a fundamental constant of it. Proton mass, we said that, right? It's all determined by QCD, quantum thermodynamics. There's nothing fundamental about proton mass. Okay? So, key idea is that if we apply the same limit to dark world, if dark world has something analogous to dark stars and dark proton and dark electron, those dark worlds are subject to different Chandrasekhar mass. In particular, if the dark proton mass is much heavier than ours, we can make the small black hole. Okay. So, to explore this new possibility, I had to have some model. So instead of having this boring single flavor dark matter, I added some flavor to dark sector. So we have dark proton X particle, dark electron C particle, and dark ENM is gamma D. So here dark proton is not necessarily the composite state of three quarks. It can be just fundamental fermion, but it's heavier, and fundamental fermion which is lighter with opposite charge. That's all I need. So in this theory, I have a couple of parameters, like dark matter, dark proton mass, dark electron mass, and then dark fine structure constant. I don't know, I mean, I don't have any limit for this one. I just set this to be less than 1. But then to make life easier, I just use it with a nominal value for our standard model EM. And then there's also a temperature ratio between dark CMB and current CMB. That is C. So the key thing, why do I need that? Because I want to have dark structure beyond the usual CDM can provide us. And then to do that, I need energy dissipation. That is the key concept here. So if you think about how we form galaxies surrounded by halo. In the early universe, when the halo first formed, we had baryons and CDM all together forming this giant ball of halo. So here the blue is CDM and red is baryon. After some time, we all know that we form galaxies at the center, and then still dark matter halo surrounding us. The key difference, what does baryon do but dark matter does not? That is cooling. The fact that we can observe galaxies means that galaxies are continuously shining, losing photons, losing energy. If you lose energy, you sink toward the center to form structures like stars and galaxies. That's why I need this energy dissipation process. And atomic dark matter model with a dark proton, dark electron, and dark UNN is the simplistic model that I can think of to realize this process. So I want to have some rich dark structure like dark matter stars and dark matter black holes. So this model is nothing new. For example, Lisa Randall, she wrote this book called Dark Matter and Dinosaurs. Her book is entirely based on the same model. Although her model has very high dark photon temperature, in this case, you expect, in this model, we expect, just like our usual baryonic sector, we expect to have dark acoustic oscillation, dark Swift damping, and all those rich phenomena. And for her parameter space, we expect to have dark acoustic oscillation very close to our baryonic acoustic oscillation, which we didn't see. So that excluded this model space. So I want to evade this bound, so I set the temperature of dark CMB very low. Very low dark CMB will bring the dark recombination at very early time. This is one of the example model space. As a function of redshift, I computed the dark electron fraction and then dark visibility function. So dark electron fraction is near 1, means that dark matters are in the plasma state at redshift beyond 51,000, very early time, and then dark recombination happens at this time and then it drops. Just like our normal CMB. I did this, I used the redshift to compute this, and I can also compute the dark visibility function to have when dark decoupling happens. It's about redshift 32,000. That brings the dark acoustic oscillation scale 0.42 megaparsec, means that it should happen like K of 50, which is well beyond the K rating that we observed so far. But yet, I want to make dark matter structure, but I don't want to spoil the already well-established cold dark matter Lasky structure. I want to avoid my model to be killed. So if I want to not spoil Lasky structure, I require that the energy comes with this energy dissipation, and there's a time scale associated with energy dissipation. It's called the cooling time. And this cooling time is different for various different halos. What I require them to do is for the halos of mass greater than 10 to 11 solar mass, this cooling time is much larger than the age of the universe, means that dark matter dissipation does not spoil already well-established cosmic web and all those Lasky structure. It is only operating on small halos to form dark matter black holes that I want. Okay. There are two mass scales. Already I told you about the Chandrasekhar mass scale, which is inversely proportional to dark matter proton mass squared. And second mass scale is called the opacity limit. It's an old argument by Reeds or the Lehman belt, and they have, so when you study the stellar formation, the gas cloud collapse, the gas cloud first collapses by the thermal wave, but then it cannot lose enough energy if the optical depth is too high. It means that you cannot lose energy because photons cannot escape. That marks this opacity limit mass scale that is determined this equation. So in the model case, 10 to 3 solar mass. Maybe you have heard that for the population 3 stars formation, 10 to 3 solar mass is sort of the order of magnitude ballpark of the stellar mass, and that is given reference to this mass scale. But then if you have different proton mass, of course this is different, and if you have different T is given by the energy level of the cooling, so that is also different. And then if you get plug in, you can also figure out the dark opacity limit mass. Yeah, and then dark star formation, maybe you have already noticed I referenced to population 3 star a couple of times, because in our theory, I have dark proton and dark electron. I want to form a stellar object. And this process is exactly parallel to the formation of population 3 star formation. Right? So what I did for the first estimate is that we compute these two mass scales, like opacity and Chandrasekhar mass scale, and then we went to the population 3 star literature. They have run many simulations, and there are rich literature about population 3 star binary statistics. Right? I took those, and population 3 stars mass function, I took those, and then I turned it into the prediction for the gravitational wave sources. So this is one of the results in our earlier paper with Sharon Sandera and Henry Gephardt. And as a function of dark matter black hole mass, we compute the mass function. That is, we took the population 3 star literature and then get those numbers. And then also we have distribution of the mass ratio and the semi-magnetic axis. All of them can turn into the gravitational chirp mass and then the horizon size of gravitational wave detection as a function of chirp mass. So this is a 1% of solar mass to solar mass. And then the lower line is for the advanced light current means as of 2018. And cyan is the advanced light of the full upgrade. And then blue is Einstein telescope. So if you are focusing on the 10% solar mass dark matter binary, you can reach out to, say, a couple of tens of megaparsec. So there's one event within the 20 megaparsec boundary of 10% of solar mass black holes, we can detect them. So we have made this table for various different dark matter models. Then we expected for the 2018 LIGO for this model like 1 to 100 event, 1 to 100, because just like not every baryon particle ends up in stars, not every dark matter particle necessarily ends up in dark matter black hole. So there's a fraction of dark matter black hole in total dark matter reservoir, and then among them, some of them only will form binary. So we have this whole question between 10 to the negative 5 and 10 to the negative 3. Again, we look at the baryonic simulation to get this number. So how much of the baryon is locked in the star and then locked in the binary. So that goes between 0.1% of 10 to the negative 5. So now not all dark matter has to be in the black hole. So even though we have 0.1% of dark matter in the black hole, or 10 to the negative 5 of dark matter in the black hole, we expect a 1 to 20 event from the advanced LIGO per year. Okay, so that was the prediction. Then we went back and then see the recorded event. So if you go back to this graveyard pie chart, and there's one of these orange couple that is famous, 1708-17. That is for sure the two neutron star colliding event, because we have at 1.7 seconds after this event, we saw the gamma ray signal observed by Fermi and integral. But there's another event, GW190425. That's this. They are pink, they are orange just because their mass is lower than 2 solar mass. we have no electromagnetic counterpart of this event. And if you look at the numbers, it looks a little bit weird. So M1 first mass is about like 1.5 to 2.5 solar mass, and 2, the second mass is about 1.1 to 1.6 solar mass. All of these three possibilities are possible. Okay? But people yet call this binary neutron star because they're lighter, and then the lowest black hole that we can make from the full evolution. This seems really weird. If you compare the total mass of these two binaries to those so-far observed X-ray binaries so far, so these are the distribution of galactic neutron star binaries we know. And that is the 5 sigma away. To be fair, this is X-ray selective distribution, and that is gravitational-wave selective distribution. So we always have to keep in mind the selection bias, but it's intriguing enough for us to go out to study this possibility further. And then, in this mass range, some people ask me, can that be a primordial black hole binary? Answer is negative, because in this paper, they studied this interesting fact that if these two binary systems are formed, if the above solar mass binary system will form as a primordial black hole, and then the density fluctuation in that particular scale must be very large. And those large density fluctuations, as Misao said the other day, will generate the gravitational wave. And that gravitational wave in the primordial universe is redshifted conveniently to the pulsar time array range. And then we didn't observe any PTA result in 2020. Based on that fact, they draw the fraction of the limit for the PBH fraction at that mass range, which is pretty low. So it cannot be a primordial black hole. So we went up and with our Penn State colleagues studying LIGO, so we had come up with this graph, this constraint graph. If 190425 is a dark matter black hole binary, what's the implication? Right? And then we plotted the minimum mass of dark matter black hole population, and then fractional dark matter in the black hole. So that one event can make this contour. With that one event, we can constrain the fundamental fermion mass to be greater than 0.96 GeV if you stay the same. As you claim, if you were the dark matter black hole binary. Of course, the official statement of LIGO collaboration is not, and we just have a limit. But Sarah Chandra and myself, we are on the MOU with the LVK collaboration. It's kind of weird, the whole collaboration with two people MOU. But we work together for the interpretation of subsolar mass channel detection. The official statement is that we don't have detection, but we have this limit. But it's very interesting possibilities. And then still we renew our contract, MOU for the 04A detection, so we are working together with the LVK team to search for the subsolar mass black hole binaries. Right. So the important concept here is cooling. Right? And then for cooling astronomy, you immediately think of this cooling function. Right? Cooling is the energy dissipation rate as a function of temperature. Right? So here is kind of a model cooling function as a function of temperature. I only included the atomic cooling here. And temperature is the representative of the particle state. Right? Then you can relate you can associate temperature with the virial temperature. Right? Virial temperature of 10 to 8, 10 to 9 Kelvin, that's something like cluster scale. And virial temperature of 10 to 6 Kelvin, that's a galactic scale. Virial temperature of 10 to 4 Kelvin, that's called 12 galactic scale. So the cooling function that I must introduce to form dark matter black hole, right, can have some implication of other astronomical phenomena that we have in cluster. For example, we have bullet cluster, and then this cluster cannot be completely destroyed by the collision. That has this limit, and then if you are to form black holes, the halos cool most efficiently in this mass range, and that's this limit. And then the dwarf galaxies may collide, and they may get rid of all dark matter because we observe sometimes dark matter list dwarf galaxies. They can have this constraint. So there are various other astronomical phenomena that can give us some information about this cooling function. What I mean is that this cooling function is not completely free. The fact that I want to have this dark matter black hole doesn't set me free. I have to be constrained by those astronomical phenomena. So I want to be more realistic. So with my students, I decided to compute this cooling function for the atomic dark matter model. It turns out to be very, very hard. So what I did, instead of starting from the Schrödinger equation and then get all the cooling rate, what we did, so we took the literature and then found the equation about the cooling rate, and then we figure out how individual cooling rate or interaction rate must be rescaled if you rescale the proton mass, electron mass, find such a constant, and those fundamental physics parameters. And then we managed to figure out how to do that, and these are the results. And then particularly atomic part is also easier, then molecular part is hard. And then molecular part was worked out very well by previous study with people studying population tree, again, star formation. Those are the results that we started from. And this is a usual cooling function that drops at 10 to 4 Kelvin because we don't have enough free electrons. But then if you include the hydrogen molecule, cooling function extended down to lower temperature. That's the feature. But then these three curves are the cooling function corresponding to different atomic dark matter models. Why do I do that? Because at the first guess, at first estimation, I used the top 3 literature, but I don't want to rely on this forever. So what we are doing right now is to set up all the relevant physical information so that we can run our own atomic dark matter simulation for dark star formation. And after having cooling function, what we can compute it is a phase diagram. So for those of you who follow the phase star formation again, knows that this phase diagram of the number density and the temperature is very important. You first have, initially, your halo is heating by a collapse, and then cooling happens, and then you have loitering phase, and then you adiabatically heat again. So that curve we can also compute because now we have the cooling function. So we have relevant atomic and molecular physics that we can plug in to the simulation of dark matter star formation. And then as for the cosmological simulations, we have to know the initial conditions, right? And the initial condition comes with 2 parts. First one is the electron fraction. So to form a molecular hydrogen, we have to have catalytic electrons to form H minus, and then H minus and H collide to form H2 molecules. So this is the result of solving something like a rack test I showed you earlier. There's a residual electron fraction after the recombination. That's the computation that we did. And right-hand side is the initial matter power spectrum. Must also be modified. I said the dark recombination happens for this one model at redshift 50,000, right? But then there's a Sick damping and then dark acoustic oscillation operating that will suppress the dark matter power spectrum on small scale. So basically, small scale small on the horizon side at the time of recombination. That's basically the Sick damping scale. So we compute those, and then now we are ready to run. We are testing the Gizmo and Ramses code to run these simulations. And then while running the simulation, I don't want to blindly believe what we are getting from the simulation, so I estimated some properties of the atomic model. And then here, we figured out that because this chemical evolution does not supply the density evolution, so we have to assume some density evolution. And then density evolution must be bracketed between the hydrostatic equilibrium or just adiabatic collapse. And for each case, as a function of that proton mass and that electron mass, we computed the regional parameter space where we form enough number of dark molecular hydrogen. Because dark molecular hydrogen is a key element to form small stellar objects in this model. And as a byproduct, with my student James Gurian, and then Liu, we actually take a look at the top 3 star formation. Because now we have cooling function and we know the halo statistic. It seems like we have all the ingredients required to model population 3 star formation. And there was this paper by now Yoshida's group in the Hinano level 2013 paper. They ran large cosmological simulation followed by small relative hydrodynamic simulation, and they had plotted as a function of formation ratio and then real halo mass, what must be the resulting the top 3 stellar mass here. And then in that paper they had this analytical expectation, this curve. But then in this paper we use a simple time scale without integrating anything. I only use algebraic equations to have this color-coded plot. And I think, maybe it's only to my eye, our color coding matches better than their analytical expectation. It's kind of success. Within a factor of few, we could reproduce the distribution of mass of possibly star as a function of redshift and the halo mass. That was a fun side project I had. And when the stage right now is we are ready to run the embodied simulation, and then now we're testing the various code input and output using this analytical expectation of what atomic dark matter must be. Okay, so let me conclude here. The gravitational wave can provide exciting new way of studying the dark matter physics. And then here, I really emphasize that we are using, so unlike the particle theory experiment, one guaranteed interaction of dark matter with gravity. And if this event, 1904-5, is a dark black hole binary, then we conclude that dark proton mass must be heavier than standard model proton mass. That's the zero solar constraint. Of course, if you include the cooling function, all the complicated calculations, you can extend that constraint, but we didn't do it yet. Also, we can combine this with other astronomical constraints because this whole thing comes as a cooling function. The cooling function involves as a cooling at different temperature. Each temperature is corresponding to different astronomical object. And so my search is ongoing with the LVK collaboration, and we started like May last year. So please stay tuned. And my last slide is at PS, we are hiring postdocs and junior faculty. So it's very weird because of bureaucratic reason, you have to apply through this website. So if you're interested or if you have some strong candidate, please encourage them to apply. And there are 3 jobs, and one is astrophysics postdoc, and then another was QC fellow, that's like non-tenured assistant professor kind of job. And then we have 2 positions in department in the physics, school of physics. But then applying one of them does not automatically roll over to another. So if you're interested, please apply. Thank you very much.
Thank you. Anyways, questions? Good.
It's fantastic. Your model is fantastic, so original. But I just have one question. So in your model, so it's like kind of counterpart between dark and the baryonic particles. So what about neutrinos? Do you also have this dark neutrinos? Neutrinos are dark, but I mean counterpart neutrinos.
Yes, I could. I mean, there is a model called the mirror dark world model. That model, we have really one-to-one correspondence between dark world and the real world. But we could use that model. But in this model, to make this model more tractable, we just simplify our dark world model. So in our dark world model, as of now, it just consists of dark electron, dark proton, and dark proton.
Okay, thank you.
George?
So do you have a dark baryon to dark photon ratio?
Right, yes, I think, yeah, sure. But then this ratio should be smaller than standard model because we want to have dark photon temperature much lower than standard CMB temperature. But then we do not want to have them equal number. Otherwise, we cannot, because if they are equal number, eta is so large, and we cannot use all beautiful results that we have in the CMB calculation.
So the constraint on number of characteristics is related by.
That's right. Yes. So dark photon temperature is constrained by number of relative species because we cannot spoil the expansion rate already constrained by CMB and BBN.
Yes. I couldn't catch up why you paid attention to the GW19 April 25 as a candidate of dark sector binaries. Is the wave form of the event how to explain by the normal black hole binary?
Yes, because their mass is less than 2 solar mass, right?
Yeah.
One is 1.5 to 2.5, one is 1.2 to 1.6. So they designate them as a binary neutron stars, but it can be anything. The reason why the official designation is not binary neutron stars is because they are lighter, right? So that's why I focus on this design. And also this graph is intriguing enough for me to explore the possibility because they are 5 sigma away from the known galaxy neutron star lines.
So is such an event by LVK observation only this one so far?
So far, yes.
I see. Thank you. Big one.
I have 2 questions. So first one is that, so obviously you don't want to screw up the Russian structure, but the dark sector, the dissipative dark matter will also have an effect on the substructures of dark matter halos. Are there already existing constraints or?
Right, yes. We don't have much structure, that's right. Yeah, that's one of the predictions about, but to get some conclusive evidence and to figure out which corner in the parameter space is consistent with that, I think I need to run an simulation.
Okay, I see. So this is not something that you can get good handle already with the analytic.
Right.
Side. Okay.
Right.
And then the second question is that I was wondering, what would it take to have a smoking gun detection of one single event of the center?
Right. I think people can still argue about the neutron star when it's around 1 solar mass, but then if we have 10% solar mass binary, and I think that would be pretty much it for me. Then I'll just drop everything else and focus on this for 100% of my time.
But I guess you need to know that there's definitely no optical counterpart.
Yes.
And then, but I guess the searching or the effort to search for an optical counterpart is so incomplete just because the localization.
That's true.
Is
But then there's another thing. I mean, I don't know if it's possible for LIGO, but for the compact object, the smaller compact objects are larger. Right? For the degenerate stars, if you are talking about 10% of solar star, that's bigger. So 10% solar mass black is small, 10% solar mass neutron star is big. So there is something called tidal deformability. So if you have 2 big objects colliding, then tidal field will deform the shape, and then will give distinct waveforms. I think that's another way of distinguishing small black holes from the small non-black holes.
Okay, thanks.
Very nice talk. Does the model, generically address any other problem? Like, for example, the other coincidence omega dark matter is 5 omega bar, roughly 5 omega bar around. Like the proton, the dark proton, does it address that, for example, or any other early universe, situation?
Right.
You get a free lunch.
Right. I talked to many people, and I've thought about this thing, but I couldn't find obvious violation points so far. So if you have something that can.
I may ask a question on universal logic and imagine that these dark atoms form dark aliens and they put a LIGO detector and then they see, and then they have their own response to the general star limits and Second mass limits, they're different, and then they see all these events and they use your logic and think therefore they exist to them, dark matter. But would they misinterpret the event rate data? Because they, like you know, they would say, oh, but therefore the proton mass in the other sector would be some number. But that depends on where they put the mass threshold on what they think is a misclassification of the LIGO detector, isn't it? I mean, couldn't they get the wrong answer with the same logic?
Let me think about it. Yeah, it's an interesting question.
Okay, yes, Jamie.
Can I ask how well do you know about the waveform of these dark matter binary black holes? Because I ask because for the neutral star, you need to, in addition to the standard GR calculation, you also need to know pretty well like the equation of the state. And like in your case, like what are the additional concerns?
Because they are black holes, and if you rely on the Moore theorem, black holes are simple objects. Right? Black holes are characterized by mass speed charge, just like fundamental black holes. So the calculation for the black hole binary waveform in this case is much simpler because there's no substructure inside.
Good. Anyone else? Well, if not, let's thank Donghui again.